Without any further ado, let's talk about our S3 API that's coming up. In our last broadcast, we talked about the way in which data is addressed on the network and the structure of how that data is being put onto the network. Let's just start with a really basic idea here. You have what is a hypergraph. And if you're unfamiliar with what a hypergraph is, it's basically the same thing as a graph, like you can see above, except the difference is that instead of an edge connecting only two vertexes, it can actually connect multiple vertexes. And what's really cool about hypergraphs is that on top of it providing a way to relate a lot of data together in a very efficient data structure, it's something that actually maps really well to a lot of other types of data structures that we would want to use. So for example, if you're wanting to do a relational database, you can express that as a hypergraph. If you're wanting to do a basic key value store, you can still express that as a hypergraph. And for our case of S3, we can actually express this as a very simple graph. We don't even need most of the hypergraph elements at all. So the way that this basically works is that when you encode data on the network, and this is actively what's happening with mainnet right now, you're encoding that data in a format that is using what's called verifiable encryption. And verifiable encryption is just a way that you can take data, you can encrypt it against a target decryption key without even knowing the decryption key. And then in doing so, that data bundle you produce is something that is verifiable in that any other node on the network can see that encrypted data and know that the target decryption key can absolutely decrypt it. And it uses a bunch of really funky math to do that, but the basic premise is that it's essentially just a clever proof structure that lets you say that this data was transformed into this encrypted format and you can verify it mathematically. So the way that it works ultimately for our S3 store is pretty simple. So when data is encoded onto the hypergraph, we have two types of objects that we're dealing with in terms of network structure. There is a vertex. A vertex is obviously a point, and then a hyperedge, which is an edge that connects multiple vertices. And that vertex basically contains a blob of data that is an encoding of a Verkle tree. And so we talked about Verkle trees in the last broadcast, so I'm not going to deep dive it too hard, but the basic idea is that when we're encoding data onto the hypergraph, we are basically saying that, and keep in mind, like the actual vertex is, sorry, not the vertex, the tree structure is actually 64 leaves and branches, so the degree of the tree is a little bit different than what I'm showing here, but it would be very hard to actually graph this all out. So the basic idea is that we have this section of data. Oh Lord, what have I done? Let me try and rotate this so it's a little bit less messy. Pardon me, I'm not the best with Excalidraw. I just use it for quick sketches to walk through this. But essentially you have a tree that is a collection of nodes, and those nodes, are either branches or leaves, and those leaves at the end contain the actual chunks of data. But those chunks of data are verifiably encrypted data. So we have each segment of data, 54 bytes, encoded into each leaf. Now that's 54 plaintext bytes. The data that's encrypted is a little bit higher than that. Let me do some quick math. It is 113 bytes. So 113 bytes for every single leaf, and those roll up to a commitment, and then the commitment at the branch level contains the total commitment over that entire range of leaves, and then the node, like the root node, contains a commitment of all of those commitments. And what's really cool about that is that gives you a way, because of the way that we are actually encoding that data, it gives us a way to prove any of the data in there, and you can even prove some properties of the plain text of that data as well. Not too useful for S3, but it comes into great use for some other applications. In the case of S3, we're just basically chunking the data into little subsets, putting them into the leaves of the tree, calculating the commitment, tossing it into the vertex's root value, and then those chunks of data are ultimately collected as a series of vertices. Now, the total size that a data shard on Q can have is up to 1 gigabyte, and S3 allows you to have multiple gigs of data. Like I think there is an upper limit, but that upper limit is incredibly high. And so in order to support that type of functionality, we actually have another chunking mechanism that chunks the data into smaller concrete sizes. Like instead of being 1 gigabyte, because calculating the commitment on that is actually rather expensive, we actually chunk it down into smaller sizes, around 256 megs per given chunk of the file. And then finally, we have essentially what is so we have chunk 1, chunk 2, chunk 3, chunk 4. And then finally, we also have a metadata chunk, and that represents the entire collection of information necessary to represent an object in our S3 compatible API. And that's basically it. It's just a get and set, and of course a delete if that data is being removed. And then regarding the encryption and decryption of that data, the way that we surface that is through the use of those one-time keys. So if you produce an object on S3 and you're not using a public bucket, in other words, you're using those signed, I forget what it's called. It's basically a signed file request. It has a signature that is an HMAC for AWS, but it's realistically just an opaque blob, and most things do not actually expose the inner workings of that HMAC. And so for the broader, broader tooling around S3, we don't have to worry so much about the compatibility of that because it just treats it as an opaque blob. And for our use case, we use that opaque blob in order to store the decryption key. And so when you're producing that output and you're wanting to actually get the file out of it, instead of doing a normal signed request where you're validating that you are authorized to access that file, instead you are providing the chunked data necessary to decrypt that file. And by doing so, you then get the file. And so it's kind of a neat trick. It's a little clever hack, but it makes us compatible with all the S3 tooling that exists out there. And so I could give you a demonstration of S3 tooling, but that is like the most boring thing in the world. So instead, I'd rather get into the next topic, which is the KMS API. And the cool thing about the KMS API is because it starts to actually show where Q shines. And back to our original thing we were talking about with the news, it gets into the heart of what some companies are doing wrong and how Q could potentially save them as much as it also is just a really useful thing to have on the network. And so when we talk about key management, there's a lot of companies out there that are creating wallet as a service type integrations. So in other words, I'm not going to name any names of them because I have some interesting opinions about all of them, and I'd rather keep those opinions to myself. But a lot of them follow this notion of essentially taking the key, and they will do one of two things. Actually, one of three things. They will either split the key into a bunch of shards, and that shard split happens sometimes on the client, sometimes on their backend services. And then those shards will be distributed. In the case of some popular ones, they will take the shards and usually they'll do a 2 of 3 threshold split, and they will take like shard 1 keeps local on the user's device, shard 2 they send to their given infrastructure, in shard 3 they will sometimes have an optional local backup that's encrypting that data, or they'll have an encrypted backup in their own infrastructure. That's option 1. Option 2 is that they will actually do multiple shards, and those shards will be created inside of a trusted execution environment, which gets back to what I was talking about earlier. And they might give you a shard, or they might not. They might have multiple TEEs. It just kind of varies by implementation. And then there is also a third, which is no shards at all. They are just YOLOing keys into their database using just some encryption key that is likely TEE backed. A lot of them will use a TEE for some degree of defense in depth, but it is essentially a singular key that is protecting all of the keys of their customers. And a lot of them won't tell you about that in their documentation. And in fact, some of them will go as far, and I'm specifically meaning the case of not encrypting keys in multiple shards, not giving any shards to the users, nothing. It's just a single key in their database that's encrypted and stored, and then they just use it in a TEE. They will still label this as non-custodial. And this is what I was getting to about with respect to jurisdictions. While the UK is obviously doing something cuckoo for Cocoa Puffs with this whole like forcing Apple to give over encryption keys nonsense, even in the States, if you are operating in the United States, especially the state of New York, because they're really picky about this, if you are operating in the United States and you have customers' keys that you are holding on their behalf, and it does not matter. It doesn't matter if you're combining it in a TEE from shards that people are sending to you. It doesn't matter if you're holding it in the full key format. Either way, your mathematics don't matter at all to the state of New York. According to the Department of Financial Services for the state of New York, that makes you a custodian. So not only are they lying to people, they are also breaking compliance laws. And their basic premise here is that, well, they're not big enough to get caught. Well, that day's coming soon for a lot of these folks. So what makes Q unique is that the way that we actually do key shard management and key management in general is that the key shards are independently held by the individual users, and the actual steps of doing signing is done using an MPC scheme instead of using a trusted execution environment, compressing all that data into the actual key, signing it, putting out the signature bundle, and then erasing all the memory of that particular execution environment. No, we are actually doing MPC, where the output is a signature and it only occurs mathematically from each of these individual machines, whether it's a user's own device or a node on the network, is collectively producing that signature together. You can kind of think of this as a concert. In other words, these devices are different instruments in a grand symphony, and only when you hear them all together, you get the beautiful music that is a signature output. Whereas instead, what they're doing is they're basically YOLOing an MP3 into a garage and playing it out, and then recording that recording itself and playing that back to you, which that is nowhere near as safe, nowhere near as sound. So I'm going to actually go ahead and demonstrate that so that people can understand how freaking easy it is to use these things on Q. So we'll go ahead, and I have an example of a KMS API. I'm going to spawn it with only 2 signers, and I'm going to use the preset account that's holding some keys. And I'm going to go ahead and actually create a key. And as you can see here, this is the AWS API. The only difference is I'm pointing the endpoint to the KMS API. And so what we're going to do is we're going to create a SecP256K1 key, or in other words, a Bitcoin or Ethereum key. And we're going to just run that. And you can see that it creates a key task. 2 different parties pick up on it and then complete the operation and create the key. And very similarly, let me go ahead and, where's the public key? I did these all in advance because I can never remember the full CLI. Let me grab that real quick. There we go. And so we'll go ahead and grab the public key and use the key ID, and note that this is in the AWS KMS format. And there you go, you get your public key output. Great. So then let's go ahead and do some multi-party signing with it. So let's go ahead and create a signature request. And so this is going to be the fun part. One of the things that the AWS KMS API doesn't do is it doesn't actually support some of the things that Q's KMS API does. And so one of the things that people deal with for key management, where they're using services like AWS KMS to handle their keys, which is a bad idea, or using Cloud HSM or other options to handle keys. A lot of them do not actually support the native signing formats of those particular, networks. Like Ethereum, for example, uses Ketchik 256 or SHA-3 256, if you want to call it formally. It doesn't use those at all, and so you have to kind of pigeonhole the data in the right format. And what this means is that the KMS API, for example, lets you sign either the raw message, where it does the hash inside of the KMS service infrastructure, and then produces a signature, or you can pass it the hash. What's dangerous about that is that there's a lot of things that can go very badly if you can just pass raw hashes to the KMS API. So in the case that the KMS API is compromised, for example, when you, if it were compromised, all of those keys then become able to have any hash sent to them and any hash sign, which means that they can do any signature operation for any of those keys, and potentially, like drain a wallet or whatever. What's unique about Q is that you can actually choose to enforce which operations you do allow. So whether it's a SHA-3256 signature or a SHA-256 signature for Bitcoin, or more specifically, adding further additional rules like I will only allow signatures for this given key if it follows whatever structural format. Now we don't expose this obviously through the KMS CLI feature. That's just something we can't do. But when you go into the Q console, you can actually set those kinds of rules. So that gives you a really rich, really deep set of rules that every party has to adhere to, or the key does not get used to sign. Like you cannot construct the signature. And what's great about that is we do not have to worry about custodianship, because the user holds the key, the other user holds the key if it's a 2 of 2, the infrastructure of somebody calling that service. So if a wallet as a service company wants to actually go make themselves compliant, they can go use us. And then their user can pass in their key shard, they can pass in their key shard into Q's MPC infrastructure and get the signature output without having to trust a TEE and worry about, having to give the keys to the castle, literally, to regulators. So we have this, we have our ECDSA SHA-256, so Ketchik 256, we have a message, it's a hello world. Let's change this to Ethereum's hello world computer, LOL. And then we'll base64 encode it, because that's the format that it expects. We have the key ID set, and now we have a signature. And so the next thing we're going to do is and you can see the parties involved to their signing operations. And so the next thing we're going to do is we're going to verify that signature. And the neat thing here is that I got shit in the way. Hang on. There we go. Okay, so the next thing we're going to do is we're going to verify it. So we have all the data we need here. ECDSA SHA-3256. Let's change this message to hello world computer, LOL. And then change our signature to the output signature here. And you can see that the signature was valid, and we can test against this. We can also, put in a bad signature, and now the signature is not valid. Or we can change the message itself, and you can see again the signature is not valid. So just like a traditional KMS API, you end up with the ability to sign a message and do all the normal KMS operations. The next thing that I also want to bring up is not only do we have like additional signing algorithm options like SHA-3256, but we have additional keys that KMS doesn't support. So ED25519, in other words, if you are working with Solana, for example, and you need to manage keys for that, again, it does MPC key construction, and you can do signatures on that. And we'll just go ahead and use the same message. Oh, I think this will return an error because I don't have the new key ID specified. Let's make sure. Ah, yes, they completed and aborted, which is why there's no key or signature completion, and you end up with a incompatible signature type. So like I was saying, you can't even force them to do things they're not supposed to do. Let's paste in the key ID here, and we end up with our EDDSA signature. Let's go ahead and verify it real quick and make sure that that worked. And then change our signing algorithm to EDDSA 25519. And we have a valid signature. And like before, let's go ahead and change this to something else, and we can confirm signature is invalid. Okay, so that's basically it. That's just MPC-based signing, and it works exactly the same way people come to expect it. Deployment, there's a little bit of tricks to it, but it's basically just embedding a JavaScript SDK for a web app or another language-oriented SDK if you're using like native code. If you're doing like a mobile app and using Swift, that's fine. If you're using Kotlin on Android, that's also fine. But that's it. That's it. And you end up with multi-party signing for any given key, and that's basically it. Let me go ahead and also mention one more key that it does support, because this is something that is very relevant now for Q. ED448. Because keys on Q use ED448 keys, we do need support for that baked into this API. So if you want to, for example, have an MPC Q wallet that some number of parties have to all co-sign together to move funds, this is a great way to do it. It also gives you the option that, like, for example, when you're running a node and you want the rewards to go to a given key, but you don't want that key to be hot, you can use the KMS API in order to produce these MPC keys so that you don't have to worry about, if that node were compromised, for example, that those funds that were accumulated by running a node were lost. And so very valuable thing there. And like before, we'll just go ahead and sign this. And the funny thing is, I have this Hello World Wide Web. If you look at the Q website, we actually, like if you look at the historic data around it, we actually had that slogan before Ethereum did their Hello World Computer. I'm not better. And there you go. Oh, did I miscopy the key? Well, that's funky. I must have done something wrong. Anyway, basic premise is that you create a key, you sign with the key, and you end up with your outputs, and it lets you do it in a way that doesn't you don't have to worry about key compromise in the same type of situation as before. And so yeah, those are the two things that are going to be coming up in the next couple days for the public preview, as well as the final release for 2.1 itself. Then those will be live on mainnet as addressable applications that you can use with or without the broader KMS style APIs. So if you want, more complex rules, you'll be able to log into QConsole and deploy those rule sets to your given keys and apply them accordingly. And so yeah, that basically wraps things up. I'll give it a few more moments for people who might have any questions, anything that you want to talk about, but it's nice to actually see one of these streams basically end in less than an hour instead of running for 2. Let me make sure I'm not missing any questions on Twitter. Cool. All right. So yeah, that basically wraps things up. Oh, plans on hiring anyone for the team? Yep. I will talk more about that soon. That's all I can say about it for right now. So that wraps things up. If there's any other questions real quick, I will be happy to answer them to the best of my ability. But does S3 handle Git? No. But that being said, if you actually wanted to take an application like GitT, this is one of the applications I was wanting to convert into a service on Q. But if you wanted to take an application like GitT and then convert their level DB implementation to target the hypergraph instead, you would basically convert the GitT application into a decentralized app that is Git compatible for not free, but yes, beacon decommissioning. I guess that's fair to mention. So for people who haven't been in the testnet channel, with the final phase of milestone 5, and then the broader release of 2.1 on mainnet, the beacon will be finally decommissioning. The way that works is going to be a 2-step operation. So in other words, 2.1 is released, and then in order to continue keeping the network moving forward, it will continue to produce frames for a short period of time while it's converting the entire store of the network into this encrypted hypergraph format. And once that is completed, it will then send that to the rest of the network and then basically sign off. When it signs off, the network will become fully decentralized in every single way, and nodes will be collectively building the network instead of relying on a centralized sequencer of the beacon. One thing that's kind of important to understand if you're not familiar with why the beacon had to exist in the first place, when we were doing the pre-2.0 era, like the 1.4, 19, 20, 21 versions, the proofs that were accumulating were so massive in terms of overall size that it was actually consuming, like if we were to have the network hold all of the data of those proofs in order to fully reconcile them, it would have actually been like, if I recall correctly, I don't remember the number specifically. I want to say it was like 250 or 300 terabytes of total storage used on the network, which would have basically cut emissions to practically nil immediately. And that would have been a terrible experience for everyone involved. And so this was basically our way of working around that. So yes, the beacon will be decommissioning at the beginning of 2.1. The 2.1 release will basically let it produce the encrypted hypergraph, and then at the target frame for the true cutoff of the network into 2.1, it will then begin that process of syncing that hypergraph to everyone on the network, and then collectively the network will move into full 2.1. There is one additional note. If you do want to actually run the node in true verifier form and calculate that same hypergraph yourself as a way to just like further add resilience to anything that could go wrong, you're totally able to do so, and we will have steps on how to do that. But this is just something that there are some nodes out there that would take so long to actually produce the hypergraph that they would basically be locked out of actually joining into all the new shards that are being created and actively participating. They basically get screwed out of being able to operate on the network at the same caliber that some of the other nodes would. So this is kind of our final compromise to get rid of the beacon. When will quorum public links be totally operational and sync? That is the next thing that follows. Like that's the thing, like the S3 API, the KMS API, those are all the next things that we're rolling out. Fixing the public links is equally prioritized. We will get that solved as fast as possible. Was there any demonstration of the S3 API? No, there wasn't really a point to. It's like much more boring because there's no crazy MPC involved. It's just encrypting data and putting it in a blob. And so you'd literally look at me using an S3 tool with no real cool things to show, unlike the KMS example where we're actually dealing with MPC. But yeah, those things will be made available this week, and I look very forward to people putting their apps on it and seeing all the cool things that people come up with. Cool. So I think that just about covers it. If there's any other questions, then feel free to ask. But otherwise, I'm going to wrap this up. All right. Awesome. Well, thank you all for watching. The next weekend, the next Sunday stream, this time will actually be a Sunday stream if my ISP doesn't fail on me like it did today. The next Sunday stream, we're going to be covering a lot more interesting news, so I'm really looking forward to that. Cool. All right, everybody, I will catch you all on the next stream.